Hello. In this video I will show you how to use curved arrows to explain how electrons move in individual steps in a mechanism. So basically we're going to be looking at an individual mechanism step. As you know, there may be one or two or three or even more steps in a particular mechanism, but we're going to focus on a particular mechanism step, and we're going to explain how the electrons move from one place to another, to form bonds, to break bonds, to make lone pairs or use up lone pairs, those sorts of things, and also how charges get formed and get used up in a mechanism step. Curved arrows is just a formalism. It's a way that chemists explain how the electrons move in a mechanism. When you see a curved arrow with a double-headed arrow point on it, so here's the arrow, double-headed arrow point, that means one pair of electrons, two electrons moving from one place to another. So how can they move? Well, it could be that you have a pair of electrons on one atom, as a lone pair, moving into a position between two atoms, so it becomes a bond. Usually the atom that the lone pair was on is one of the two atoms that become bonded. We'll see examples of that in a minute. Or a pair of electrons can move from between two atoms as a bond to being on one of those atoms as a lone pair, sort of the reverse of number one up here. Or a pair of electrons can move from between two atoms to between two other atoms, so breaking a bond here and making a bond over here. So a bond becomes a different bond. Or combinations of the above, in that in some individual mechanism steps you may have two pairs of electrons that are moving at the same time, or three pairs of electrons that are moving at the same time. So it can become a little bit complicated, and that's where using curved arrows can be very useful to keep track of what electrons are moving where in a mechanism step. So here's just some examples. This is a generic case where I've got some atom I've called X with a lone pair of electrons on it, some other atom that I've called A without any lone pairs on it, and this curved arrow then suggests that that pair of electrons is going to move in here between the X and the A, and it's going to become a bond. And so there's the bond that the lone pair started out as. It now becomes a bond. And of course in the process, the X atom has essentially given away one electron. It's taken a pair that belonged to it by itself, and it's now become a shared pair, so in essence it's giving away one electron, so it becomes positive. And at the same time, the A that didn't have either of those electrons now has one of those two because it's sharing that pair, so it becomes negative. It's essentially picked up one electron. So this is a sort of a generic example. Here's a real life case. So this is a carbocation. It's a carbon with three hydrogens only, so three bonds to carbon. So because it only has three electrons instead of its valence of four, it has a positive charge. So this is called a carbocation. Here's a lone pair on water. If this CH3 positive encounters this water molecule, that pair of electrons moves in here between the oxygen and the carbon to form a new bond. That's that bond right there. This pair of electrons that was there is still there, but this one is no longer there because now it's part of this bond. And in so doing, this oxygen has essentially given away one electron, so it becomes positive. The carbon has picked up one electron, so it goes from being positive to being neutral. So the charge balances. We had a positive there, and now we have a positive there. By the way, that positive is actually on the oxygen, not on the hydrogen here. Okay, so here's another example of a lone pair becoming a bond. Here's another example. This bromine, of course, being negative, has four pairs of electrons on it. If one of them moves in here to share with this H+, we'll have a new bond in there. And I'll let you take a minute, we'll stop the video and see if you can predict what would be the structure of the molecule that you would get by following that curved arrow right there. One other thing you should notice here is that in order to clearly show how curved arrows show the motion of electrons, you really need to draw in the electrons that are important. So notice that this is actually a Lewis dot structure, and it's showing the lone pairs. Now I haven't shown the two hydrogens and their bonds explicitly because they're not really entering into the reaction, but I have shown that bond explicitly because it is part of the overall reaction. If you're going to do curved arrows, you need to do two things. You need to make sure that you draw the molecules to begin with next to each other in such a way that any atoms that are going to become bonded to each other are right next to each other on your paper. So I drew it on purpose so the oxygen and the carbon that I knew were going to become bonded to each other are next to each other on the paper. It wouldn't make any sense to draw the water like over here with OH2 and then draw this carbon over here, because then the oxygen and the carbon that we know will become bonded to each other aren't close together, so there's really no place to draw an arrow to. And the other thing, like I said, you really need to draw out the lone pairs if they're going to be important in the reaction, and you really need to show explicitly any hydrogens or other atoms that are explicitly going to become bonded or lose bonds. What I want you to do is do exactly what I just said. draw this molecule and this molecule in such a way that any atoms that are going to become bonded to each other are drawn right next to each other on the paper, and so we can draw a curved arrow to that place, and also draw out any carbon-hydrogen bonds, or any other bonds for that matter, with an actual dash between the atoms. So in other words, if you're going to draw a curved arrow showing a bond moving to another place, you really need to draw out that bond so that you can draw an arrow from that bond to wherever it's moving to. So take a minute and redraw these two molecules in such a way that whatever atoms become bonded to each other in the products over here that weren't bonded to each other on the left-hand side of the arrow are drawn right next to each other on the paper. So here's your answer. What I did was I took this molecule and redrew it here. I took this molecule and drew it underneath. I could have drawn it on top or pointed up and down, whatever. So this hydrogen is right next door to that carbon on the paper. So see, they're very close to each other on the paper. Why did I do that? Well, looking carefully at the left-hand side and the right-hand side, again, scanning your eye back and forth, notice what's actually happened here, what's changed. And the first thing you may notice is that that double bond isn't there anymore. It's now a single bond in here. And that was a CH is now a CH2. So in essence, that carbon is picking up a hydrogen. That double bond is becoming a single bond. That CH is becoming positive. And then this molecule, if you'll see that this oxygen-hydrogen bond is breaking, so it's not there anymore, and this oxygen is becoming negative. So this hydrogen must be coming bonded to that carbon right there. So I redrew this, and then I redrew this underneath it, so that that hydrogen is right next to that carbon on paper. Notice also I've drawn that pair of electrons explicitly because in the product it's going to become that right there. That bond has to break for the reaction to happen, so that pair of electrons must go somewhere. And so we draw the hydrogen, we draw out that bond explicitly, and then also notice that in the product, although it wasn't shown here, I drew a single bond in there because that double bond is becoming a single bond, and it'll be useful to see how does that double bond become a single bond. That's really the kind of thing that curved arrows help you to do. Example 2. Other way that pairs of electrons can move from being between two atoms as a bond to being on one atom as a lone pair. So notice that in this case I have the X and the A bonded to each other. Again, these are just generic atoms, just in general. If you have one atom bonded to another atom with a lone pair, and perhaps a positive charge on one of those two, then that pair can move out of that position onto this atom by itself. So no longer has a bond between it because that pair's moved out of there. Now there's a lone pair on this atom because that pair has gone from being a bond to being on this atom by itself, so it becomes a lone pair. And in the process, of course, by moving that pair of electrons out of there, you've essentially ripped away one electron from the X, so it becomes positive. In essence, you've given that one electron to the A, so it becomes neutral. Since it was positive to begin with, now it's becoming neutral. So this is just an example of a pair of electrons moving from a bond onto an atom. Here are some real-life cases. So this pair of electrons between the CH3 and the NH3 is going to move on to the nitrogen. That's what this curved arrow suggests. And so that bond won't be there anymore, so now obviously they're not bonded to each other. There's no dash in there. But that pair has now ended up on the nitrogen, so now it has a lone pair that it didn't have before. And also, the carbon that had 4 bonds to it is having 1 electron ripped away from it, so it has to become +1. And the nitrogen that was positive is now going to become neutral because it's being essentially given 1 extra electron from this bond that it only had 1 before. And notice that the net charge on the side is +1, the net charge on the side is +1. Now here's another example for you to try. What would happen if we took that pair of electrons and moved it onto that oxygen? That's what this curved arrow is suggesting. The oxygen already has 2 pairs of electrons on it. This is going to become another lone pair on the oxygen, so now there's a hint it'll end up having 3 lone pairs on it. That bond won't be there anymore, and this hydrogen will end up positive. The oxygen will end up negative. So there I've given you the answer, but you can go ahead and try doing what this curved arrow suggests. Let's move on. Here's another example. A bond can move from between 2 atoms to an adjacent position between 2 other atoms and become a new bond. So notice that in this case, again, this is just a generic example. I'm using X's, A's, and B's. Here we have a double bond between an X and an A, and a B positive is approaching. A pair of electrons is going to be drawn out of this bond and move into here. That's what this curved arrow suggests. So obviously this was a double bond. If we take out one of those pairs of electrons, it's going to become a single bond. There it is, a single bond. It's going to end up in this location between the A and the B. So it ends up as that bond right there. So that becomes a single bond. So now these 2 molecules that were separate are now bonded to each other using that pair right there. And in the process, of course, the B that had a positive charge is being given essentially 1 electron, so it ends up neutral. The X that was neutral is essentially having 1 electron ripped away from it, and so it becomes positive. And A that was sharing 4 electrons, so essentially had 2 to itself here, now is sharing 4 electrons, so it has 2 to itself, and so the A isn't really changing its charge at all. And here's an example of that. Here's a CH3 positive, again that's a carbocation like we talked about before. And here's an alkene, just a double bond molecule. If one of those pairs of electrons moves in here between that carbon and that carbon, now it's a new single bond. And so that CH3 now has 4 bonds to it, so it's satisfied. This CH2 that had 4 bonds to it still has 4 bonds to it, so it doesn't have any charge. This carbon that was sharing that pair, so it had 1 electron, is having that one ripped away from it, so now it becomes +1. Okay, and here's an example that you can do yourself. Notice that a pair of electrons is moving from this double bond into this position between the oxygen and the hydrogen. And those 2 lone pairs on the oxygen aren't affected, but we will have a new bond in between the hydrogen and the oxygen. So I'll let you complete that structure yourself. Okay, and then here's an example of combinations of the above. So what this picture is representing is that that pair of electrons is moving off of the nitrogen into this place between the carbon and the nitrogen. So that will become a new single bond. So notice there's a new single bond. This double bond at the same time, one of those 2 pairs is moving onto the oxygen. So instead of having 2 lone pairs, now it has 3 lone pairs. And this nitrogen is essentially losing 1 electron, so it becomes positive. This oxygen is essentially gaining 1 electron, so it becomes negative. So we have a net 0 charge on this side and a net 0 charge on this side. Here's another example. This one's going to look a little bit odd because we have a 3-mode ring here. But notice that this bromine has a positive charge. Now that's weird because bromines normally don't like to have positive charges. This actually is a mechanism step in a real reaction that we will learn in a later chapter. But for now, just take my word for it, this actually happens. But in essence, what this curved arrow is showing is that that pair of electrons is moving out of that position between the carbon and the bromine, and moving onto the bromine itself. So there's no longer a bond between the bromine and that second carbon, but now there's an extra pair of electrons on the bromine. So here it had 2, and now it has 3. And at the same time, this pair of electrons is moving into this place between the oxygen and the carbon. So we have a new carbon-oxygen bond right there. And this water that had 2 pairs of electrons before, now it only has 1 pair of electrons. The second one is now tied up in that bond right there. Because this oxygen has given away 1 electron, it becomes positive. Because the bromine has gained 1 electron, it was positive, and it's gained 1 electron, now it becomes neutral. So net +1 on this side, net +1 on this side. Here's one for you to do. What this is suggesting is that one of these pairs of electrons on the hydroxide is moving into here to form a bond between the carbon and the oxygen. And this pair of electrons is moving out from between the carbon and the chlorine onto the chlorine itself. So, how are curved arrows used in mechanisms? Well, each step in a mechanism can be shown with curved arrows to better explain how a particular step occurs. Doesn't have to be. Curved arrows are optional. You can write a mechanism step perfectly fine as long as it's balanced. You don't have to show curved arrows. Unless your professor is going to be mean to you and say, okay, show me the curved arrows for this particular step. Every step can use curved arrows. A lot of the times we won't see curved arrows in a mechanism step because hopefully it's obvious how the electrons are moving in a particular step. But if you're not clear on how the electrons are moving in a particular mechanism step, you can always put in curved arrows and make sure that you understand where did that pair come from, where did that bond come from, and so on. Okay, so here's some examples. This is a mechanism step. What I want you to do is look at this molecule, and see if you can figure out what's changed and if there are any curved arrows that you will add to this side. So go ahead and see if you can do that. Write on paper, draw this structure exactly as it's shown here, and draw in 1 or more curved arrows to show how it turns into that structure. If you put a curved arrow from that bond onto this oxygen, notice that that bond isn't there anymore, so that pair of electrons has to go somewhere. Where it goes is onto this oxygen, so it becomes a 3rd lone pair. We only had 2 lone pairs before, now we have 3 lone pairs, so that carbon becomes positive and that oxygen becomes negative. Okay, now we're going to do step 2 in the same reaction. So here's the starting material we just started with, and it turns into this structure right here. So see if you can show one or more curved arrows to indicate how does this structure become this structure. Again, analyze where are the old bonds, where are the new bonds, where are any lone pairs that might have been added or taken away, and show how the electrons are moving in this case. Okay, so here comes the answer. This is a little tricky. Notice that in this starting material we have a bond between this carbon and that hydrogen. Not there anymore. But now we have a new bond between this carbon and that hydrogen right there. So somehow this pair of electrons is moving in here to form a new bond between this carbon and hydrogen. So the curved arrow is drawn there, showing that pair moving in here between the carbon and the hydrogen. And so that carbon is losing one electron, so it becomes positive. That carbon that was positive is gaining one electron, so it becomes neutral. So here's our product of the second step in this particular mechanism. Now go to the third step. Here's the third step in this particular mechanism. This material that we just saw a minute ago, back up, is this material. I just redrawn it a little bit so the atoms that need to be bonded to each other are closer together than they were in this structure. But here's the starting material. I want you to show a curved arrow or more than one curved arrow that will indicate how does this structure turn into this structure. So draw that structure and draw a curved arrow or more than one curved arrow. One of these three pairs of electrons obviously isn't there anymore in this oxygen, but we have a new bond in between the carbon and the oxygen. So clearly one of these three pairs of electrons has moved in here to form a new bond between the carbon and the oxygen. That's that new bond right there. So we just need this one curved arrow to move in there. By the way, we just saw three mechanism steps. What I would like you to do at this point is go back and review the three steps. So here's step one. Just take that and write it down. Here's step two. Take that and write it down. Here's step three. Take that and write it down. And then add them all up and figure out what the overall reaction for this mechanism would be. So this four-membered ring with an oxygen is becoming a three-membered ring with an oxygen and a methyl group attached to that three-membered ring where there wasn't a methyl group before. This looks like a very weird reaction, and it is a little strange, but if you look at the mechanism, it makes sense that this could turn into that. Okay, so here's another example. Try taking this set of structures and turn it into this set of structures by drawing curved arrows. This one's going to require you to put in more than one curved arrow at a time. Look real carefully at this structure and this structure, see what's changed, see where the electrons that have moved must have come from, and where they must have gone to in order for that set of substances to become this set of substances. Okay, here we go. Whoa, look at that, three sets of curved arrows. So clearly, if you look carefully, this oxygen that had one lone pair now has two lone pairs. So where did that extra lone pair come from? It must have come from that bond right there. So we have a curved arrow going that way. This bond that was a single bond is now a double bond. So where did that extra pair of electrons in that double bond come from? It must have come from right here. So that moves in that direction. But if you do that and leave it alone, then this carbon will only have three bonds to it, and it really should have four bonds, which it does in the product. So where did that extra pair of electrons come from? It must have come from that pair right there. And then finally, here's an example where I give you the curved arrows and see if you can draw the product in a reaction step where more than one curved arrow is involved at a time. Look carefully at this structure, follow the curved arrows, see where new bonds are being formed, where bonds are being broken, and so on, and see if you can draw the structure of the product over here. So obviously, if this pair of electrons is moving in here, then that oxygen that had three pairs of electrons now only has two pairs of electrons, and we have a new bond between the oxygen and the hydrogen. So there's the new bond. This hydrogen that was bonded to the carbon with that pair of electrons, that pair isn't there anymore, so that bond is no longer between the carbon and the hydrogen. That hydrogen breaks off. Instead it's moving in there, so that means that this bond that was a single bond is now a double bond. And furthermore, this pair that was holding the carbon and the nitrogen together isn't there anymore. That's what this curved arrow is suggesting, is that it's not there. Now it's on the nitrogen. So the nitrogen ends up with a pair of electrons that it didn't have before. And so now instead of only one from this bond, now it has two. So the positive charge that was there is now neutral. It's essentially picked up one electron. And the oxygen that had both of those electrons to itself before now has to share that pair with the hydrogen, so it essentially loses one electron, and the negative then becomes positive. And that's the end of that lecture. Thank you.